Hello, my name is Rob Reynolds. Welcome to Business Calculus, Chapter 2, Section 8. Today we're going to be looking at related rates. These are some word problems, and we're going to expand on our discussion on Section 2.7 on implicit differentiation. So we're going to look at how these variables are related and then take the derivative with respect to not always x, but sometimes time. So again, as time passes with respect to time, we know this line starts here at 0, rise 2 and run 1. So here's this line. And so if this is the time, as time passes along, you can see as for each unit as time, the y is increasing. So the derivative of y is dy dt because it's with respect to time, and the derivative of 2x is 2 dx dt. So you can see that the rate of change with respect to y is always twice, that's the 2, the rate of change with respect to time. So our first example asks us to find dy dt. And we can do that by taking the derivative of the left and the derivative of y. So dy dt is the derivative of y with respect to t. That's how you pronounce this, the derivative of y with respect to taking the derivative with respect to time, is equal to 2x, well, and that's not a t, so I need to say dx dt plus 0, because the derivative of 3 is just 0. And the nice part about this is they gave me some information. dx dt is 2 and x is 1. So I'm going to plug those values in. 2 times 1 times 2. And the answer here is dy dt, which is what I'm looking for, is equal to 4. And here's the author's solution, and they have the same answer. One of the most common problems in calculus is this ladder problem that's leaning up against a wall, and maybe they give you the rate that it's slipping away from the wall, 2 feet per minute, and they're going to ask, well, what's the rate that it's sliding down the y part of the wall? And they might give you the length of the ladder or some other information. So this will probably be on a test. I can't imagine a calculus test without this ladder against the wall problem, and we'll look at that. But before we do, there's some certain formulas that we're going to have to come up with. Well, one is this formula for a circle. So we know that the area of a circle is pi r squared, and sometimes you need to know the circumference, which is 2 pi r. It's going to be no cheat sheets, and those are just going to be some given information that you're going to need to know. Back on this, when we get to this problem, I think it's going to be assumed that you know that x squared plus y squared is equal to 10 squared. We've got to come up with some formula that's relating all these variables together. And in this particular example, I think we're going to try to relate the area of a circle, and it's got a radius of 4. So we have some given information, and I think we have a formula here. Let's just walk through this together. We're going to relate the variables r and the area of a circle. And so the first thing, again, just stepping through here, is we need to remember the formula for the area of the circle. So then we're going to start with this equation that we just had, the area of a circle. We're going to find the given information. We have some given a rate. Let's see, maybe I should go back to the original problem to find the given rate. Did I miss that? Let's see if they talked about that. So here's where they give it to us. The radius is at a constant rate of 1 foot per second. So there's the given information, dr dt. It was right in front of my face. I don't think I read it very good though. So dr dt, I was too busy talking about the area formula when I should have been talking. Oh, and so there's the two pieces of information. The radius is 4 and the rate is 1. So on this slide, let's go back. The given rate, there it is, and the given radius. So the rate is 1 and the radius is 4. And we're looking for the area at which the rate at which the area is changing. Yeah. So we're looking for dA dt. So to do that, we have A. Let's go find dA dt by taking the derivative of the left and the derivative of the right. Well, remember, pi is just like a constant. It just kind of hangs out there. The derivative of r squared is 2r, and we have a dr dt. So let's plug in some of that given information. Dr dt is a 1, and the rate is a 4. I think we have enough to solve for this. If the rate is 4 and this is a 1, dA dt is 8 pi. And again, here's how the author worked it out. Probably better than when I worked it out. There it is, 8 pi. So again, the hard part is just maybe trying to come up with the formula that relates the variables together. So we worked this problem, and here's some different answers for different radiuses. And you can kind of see a relationship between those. So as you're going through, you got to find an equation. Sometimes it's really good to sketch a graph, find an equation, differentiate both sides, and then maybe do a substitution when all is said and done. This creeps up every once in a while, the volume of a sphere, or sometimes the volume of a cylinder. Kind of need to know, again, they're going to assume that you remember all your geometry, and I know you don't. So the volume of a sphere, I'm going to give this to you here, is 4/3 pi r cubed. Memorize that in case that pops up on your MyMathLab, or even a test it could come up on. So again, you need to know some of these formulas here. So this table talks about, if they talk about velocity, they're probably, distance equals rate times time. The rate is your velocity. It's your speed without direction. The volume of a swimming pool. The population is in a number. So here's what you're going to be doing in business calc: revenue and profit. And so if I want to find the rate at which the revenue is changing, of course that's going to be dr dt, and the rate at which the profit's changing is dp dt. So speaking of profit, here's a profit formula, and the given rate is going to be that dx dt. X is the selling units, and they give me dx dt right here. Sales increasing at a rate of 10 units per day. So those are the units per day. So you can kind of put that together, then I can say, oh, I think that's going to be a 10. And sometimes students have a hard time just trying to figure out what are they trying to find, but I would recommend that you kind of just write these statements. What's given and what are we trying to find? It says find the rate of the well, of course, that's dp, then dt when x is 500. All right, so let's see if we can go through and use this and find dp dt, which would be the derivative of this left side. Let's take the derivative of the right side, which is 500 dx dt minus 2/4, I'll say 1/2 x dx dt. And then I'll plug in as much information as possible through the given. Dx dt was given as 10 when x is 500, and I have another dx dt. And then I'll solve for this and get profit, at which the rate at which the profit's changing. There it is, $2,500 per day. Here's a nice little graph of what's going on here. Example 4 gives you a price. Now, that's always confusing. A small p in business is price, where a capital P is profit. They both start with P's, but we need to have it distinct because the price is given here, and they're asking for revenue. And so you need to know a formula for revenue. Revenue is X times P. So And you know that from your, hopefully, economics class. So if I have a t-shirt factory, the revenue is the amount of money coming in. If I sell 100 t-shirts for $5, that's my X is the quantity and P is the price, and that's going to be my revenue, all the money coming in. So remember though, profit, capital P, is really your revenue minus your costs. And so we're defining revenue as X small p minus your cost. So these are formulas that, again, you should know just as well as the volume formula for a sphere, which I don't know if you know that or not. So again, I would write down some given information. I would try to write down what you're trying to find. That'll help you if you just try to define your variables. And I'm going to say, well, the revenue is not given, but it's almost given just by multiplying this guy by another X. So I can change price to revenue by let's change this equation. 100x minus 0.001x squared is my revenue. And I know I'm trying to find dr dt when x equals 200, no 2,000 units. So let's see if we could take this guy and find dr dt. So the derivative of this thing is 100 dx dt minus 0.001 times 2. Let's put a 2 out there. Dx dt. And let's see. Oh, dx dt I think was given as 200. That's where I got the 200 from. Right here. The product of the rate, it's the units. The units are your x's. So that's the 200. So I'm going to plug that in and solve. 100 times the 200 minus 0.002 times the 200 hopefully will turn out to be 19,200. And it would turn out to be 19,200 if I would have taken the derivative correctly right here. The derivative of x squared is really 2x, and I drop the x term, and that x term is really another 2,000, which I didn't plug in there. So if I add, so I think this will work. So 100 times the 200 minus 0.002 times the 2,000 times the 200. I think will get us the correct answer. Let's see if the author, when x is 2,000. I don't think I took the derivative quite right. Yeah, there it is. There's that 2,000 I needed. So finish this up, just setting up a couple things. This is talking about the volume formula, which I told you you're going to need to know. That's the volume of a sphere formula is 4/3 pi r cubed. And given is dr dt right here, the rate at which it's 3. So let's take the derivative. dv dt is equal to 4 pi r squared dr dt's. And if I plug everything in, I'll get 12 pi r squared. So for part A, I'm going to let the radius be 6. So for part A, I would say 12 times pi 6 squared and get 432 pi. And for part B, I do the same thing, but let the radius be 24 and get 6,912. So again, you need to know that formula, take the derivative of both sides, and evaluate. Here's the author's solutions. I'll let you wrestle with this one. This is find the rate at which the cost is changing. That would be dc dt. And that's kind of easy because all you have to do is take the derivative of this thing, and the derivative of that is just a 0. So 1.05 dx dt, and then you just let your, let's see, is dx dt given? Yep, 250. And so you just plug in the 250. For this guy, the revenue, we've defined the revenue as this function right here. So we would just have to take the derivative of that and plug in for x. I think we have an x value right here. X is 5,000. So again, the derivative here would be 500 minus 2x over 25. So I got to plug in for both an x and a dx dt. And then the last thing that I wanted to talk to you about was that profit, which I think I've talked to you already, is the cost minus the revenue. I think I can just take answer A and subtract off answer B, because my profit is my revenue minus your cost. Wait a minute. Then I would, if it really is revenue minus cost, then I should take my answer B and subtract off my answer A, right? Well, play around with that and see if that works. I think you'll discover this 25,000 minus this guy will give you that final answer. So you don't really have to do a whole lot of work for C. I'm not asking you to find, you don't need to show me the derivatives for these. Here's that problem that I would guess would be on any calculus test. Again, the related rates is probably going to be x squared plus y squared is equal to 25 squared. That's the c squared length. And it looks like they give me dx dt. The rate at which it's sliding out is 2 feet per second. If we take the derivative of this, this is what? 2x dx dt? dr? No, this is dt with respect to, what's this r? Can I change this r to a y? Because otherwise it's x squared plus r. Let's just change that to a y. Plus 2y dy dt is equal to, well, this side squared would just give me a 0. It's interesting. So let's get dy dt all by itself. So 2y dy dt is equal to negative 2x dx dt. I guess you could have just plugged in from there, but sometimes it's nice just to go ahead and solve this guy. So let's see. This might be simpler. dy, because when I divide through by 2, I'll get negative x over y dx dt. Maybe a little bit less plugging in. So the very last thing I'm going to do is plug in this information when the base is 7 feet. Now I didn't want to do that in the beginning because you're going to say, well, that's the x value if x is 7, but it's changing. Sometimes it's 7, sometimes it's 15, sometimes it's 24. So do you agree this base is changing as this ladder is moving? So I wouldn't plug in that 7 till the end. Otherwise, you're going to lose that variable x. So now I can plug in this. Oh, and by the way, if that truly is a 7, this is a 7, this is a 25, then we can solve for y by doing what? 7 squared plus y squared is equal to 25 squared. And you can actually get a y value, which you're going to need. You're going to need both x and a y. And you need that dx dt, which is given. So use the Pythagorean theorem here, solve for x and y using x is 7, and then repeat the problem for part B, but this time this will stay at 25, but this x will go to 15, and you'll come up with a new y by doing what? 15 squared plus y squared is equal to 25 squared, and reworking the problem for 24 as well. So I think I have some worked out solutions here. Check to see if you get those. And for sake of time, I'll let you work on this last one. This is probably the most applicable problem. I hate to rush through it too quick, but it gives you a formula and with related to time. And we're going to find the derivative of this thing. 50 plus 0.70x dx dt, and then you're just going to plug in 50 times the 125 the rate at which that's increasing. 70, 1500. I'm just picking the numbers off of this problem up here. This was the 1500 is the x value, and we knew that dx dt is still 125. So see if you can't number crunch that. I think I have solutions here, and of course you're welcome to go to Blackboard and check worked out solutions as well there. Hope this video was helpful. Email me.